Okay, in this second lesson from the book, the goal here is for you to follow along with me, take notes. I'm going to suggest times that you pause the video so that you can try to answer these at certain points, and then you can unpause it to follow your work with my work or watch what I do and get a sense of how to do it, and then maybe repause it and rewatch it if you need. Okay? So in your workbook, the lesson should start here. Piecewiser is the topic, title of this. And at the first part, they give us the scenario. Rashid, just from the last lesson, taking another bike ride. He has a route that he likes to do on his own, and he's modeled the ride with the following piecewise function to represent the average number of miles he travels in minutes. Okay? So, first thing they want to do is they want us to state the domain of the function, and then what does the domain represent in context. So remember, domain means x's. In a piecewise function, we have multiple subfunctions. Each subfunction has its own domain. So the domain for the entire function should be the domain of all the subfunction pieces together. So remember, domain is always from the smallest value possible to the highest value. If we look at the domains, they're given in order from smallest to largest, which makes our life much easier here. We can see that the smallest value that x can be is 0, and it can be equal to 0. So we have a couple different ways that we can write this. We can write the domain as starting from 0 or included, and x needs to be greater than 0 up to 100, and we can include 100. So the domain for the entire piecewise function would go from 0, including 0, up to 100, including 100. Now, we've talked about doing interval notation for domains. So if we wanted to write the domain in a different way, we can say starting from the lowest point, which is 0, up to the highest point, which is 100. And then since we want to have 0 work, it's included, right? When it's greater than or equal to, less than or equal to, we're going to put a bracket. On 100 or equal to means that we can include 100 as well. So as an interval, we would write from 0 to 100, both brackets. Remember, there could be a bracket on one side and a parenthesis on another. So since they're both equal to, both sides will be brackets. What does this domain represent in context? Well, domain is x's, and we said that he's going to travel an average number of miles after so many minutes. So the domain here would be the number of minutes Rashid rides his bike. Right? All right, let's move to the next one. So number 2, what's the average rate of change during the interval from 20 to 50? So you can pause this before each of these questions. Try to answer them on your own. Unpause it to see how this works out. All right? So average rate of change is slope, if we remember, right? And if we look at these subfunctions, I mean, this one's in y equals mx plus b form, slope-intercept form. So we can see that 1/4 is the slope. Just like the last lesson that we did, we talked about not only slope-intercept form, but we also talked about point-slope form. And point-slope form, if you remember, was y minus y1 equals m times x minus x1. And if we wanted to write it as just y equals, we could move this y1 in the equation over to the other side, and we can get the equation written in kind of a transformed version. as we were calling it, if you remember from the last lesson, of a linear equation, right, which will help us move along here. But this is still linear, so this value in front of the parentheses is the slope, right? So the slope of this second one is 1/5. The slope of this third one is 2/7. The slope of this fourth one is 1/8. Since they only want on the interval from 20 to 50, 20 to 50 actually fits all together right here in this second equation. So the average rate of change would be the slope from 20 to 50, even though 20 works here, right? These are connecting together because it's a fluid motion of him traveling his distance on his bike. So we know that from 20 to 50, the rate of change over that interval is still going to be constant at 1/5. So the average rate of change over this interval is going to be 1/5. Remember that average rate of change would be, same thing like finding the slope from ordered pairs. Right? So if we wanted to plug things in and do it that way, we could. Or if it spanned across multiple subfunctions, we would need to resort to this. But this one all fits into one subfunction, so we don't really need to go any further than just stating the slope of that function on its own. All right, let's look at the next one. So the average rate of change is greatest in which time interval? Well, we already know that the average rate of change is slope. So basically, we just want to know which slope is the biggest. Now, some of these are going to be very obvious. We can see that, the slopes are 1/4, 1/5, 2/7, and 1/8. Now, we know that 1/4 is bigger than 1/5, right? We know that 1/4 is bigger than 1/5. These are very easy ones to compare. We know that 1/8 is even smaller than that, right? So of the first, second, and fourth one, we know that 1/4 is the biggest. So which one is bigger, 1/4 or 2/7? Now, of course, we could just mash them in the calculator and get a decimal, and whichever decimal is bigger would be the biggest slope. But let's say, maybe this is a question that we were asked to do without a calculator, on a non-calculator portion. So really, we want to know, is 1/4 bigger or is 2/7 bigger, right? So without a calculator, the easiest way would be, comparing. If they all had the same denominator, then we could see that whichever numerator is bigger was the bigger value, right? Here, since all the numerators were 1, right, 1 part of 4 is a larger part than 1 part of 5, so it made this comparison easier. So since we have different numerators and denominators, it'd probably be easier to make common denominators here. The common denominator here would be 28. Right? So if I want to turn them both into 28ths, I could do that. We would have to multiply the top and the bottom, right? We can multiply 7 by 4, which would be 8 28ths. We can multiply 4 by 7, right? Which would be 7 28ths. Now it's easy. If they're both the same, we look at the numerators. 8 is bigger, so the greater average rate of change would be 8 28ths, which was 2/7. So 2/7 was the largest rate of change on that interval. Okay. All right. Let's move to the next one. So again, we talked about this in the last lesson, right? 30 is the value of x, and we want to plug it in to get a value out, right? But since this is a piecewise function, we would need to know which one to plug it into, right? We don't plug 30 into every single one and then just record every answer, because each of these subfunctions has a domain. This is where we need to start. 30, which is an x value, is a domain value. So 30 needs to fit in only one of these domain values. Whichever one it does, that's the subfunction that we should be applying this to. So is 30 between 0 and 20? No, so we're not using this function. Is 30 in between 20 and 50? Yes, so we're going to plug 30 into this one. So I'm going to take this second subfunction, right? Wherever I see an x, I'm plugging in 30. Now, we can reduce these down. I'm going to do inside the parentheses, 30 minus 20, right, which is 10. And then we could say 1/5 times 10. Right? I mean, if you can reduce this down as you're multiplying, that's fine. A lot of students remember, it's 10 over 1, so multiply straight across. So this would be 10 times 1, which is 10, over 5 times 1, which is 5. 10 over 5 is the same as 2. But don't forget that it's plus 5. So 2 plus 5 equals 7. So G of 30 is 7. But they also want you to find the value and explain what the value means in context. So X was minutes. So after 30 minutes, Rashid biked 7 miles. Right? What about the next one? So again, we have an X value, 64. Which subfunction do we plug it into? That depends on its domain. 64 falls within the interval of 50 and 92. So we're going to be plugging it into this third one. So I'm just going to rewrite the third function, plug in 64 in for X. Then I can simplify this down. Right? Inside the parentheses, 64 minus 50. Right? Again, if you want to put this together in the same manner and say 2 times 14 is 28, and 28 over 7 reduces, then you can do that. You can put it together and then reduce the thing, kind of like that. Otherwise, you could say 7 goes into 14 2 times, and 2 times 2 is 4, and 4 plus 11 is 15. So either way you want to do that. A lot of students like to put it together so they're not kind of thinking too many steps at a time, and then reduce this thing down in 2 steps. That's fine. You can do it that way. Again, in context, that means that after 64 minutes, Rashid biked 15 miles. And the last one here, part C, plugging in 10. They didn't go in order, but it doesn't matter what order you do. 10 falls into the first subcategory, the first function, the first subfunction, the domain. So I'm going to plug that in here. I mean, this one's not too bad. It's just 1/4 times x, but x in this case is 10. So, I mean, this is 10 over 4, right? I mean, 10 over 4 reduces. I mean, if you wanted to say this is 5 over 2, I mean, you could do that. In terms of context, it would probably be easier to think of this as a decimal, right? Because it's not very often somebody's going to say, after 10 minutes, right, Rashid biked. We usually don't say he biked 5/2, miles. We'll say that this is 2.5, right? So 2.5 miles. Be easier to describe to somebody, right? Okay. So let's look at the next one. All right. So now this one. If you didn't notice, I mean, we didn't even use the fourth subfunction, and the fourth subfunction has 2 variables in it. I mean, they're not variables; they're constants. We don't know the constants. We're being asked to figure out what those constants are. Now, this goes back to what we were doing with the point slope form of these lines when we were graphing them from the last lesson, right? We were trying to understand that, since each of these subfunctions is an overall distance of how far he's biked, that this line will move, and this line moves in a different way, but it should connect to the previous line. Right? So if you remember how we did this in class in the last lesson, we basically said that when we graphed the first one, this second one should be built right off of the end of this one, which should make sense because in this setup as a point slope version, the point 20 and 5 is our x-coordinate and our y-coordinate from our point slope form. So if we look back at point slope form, right, this value is the x value of the point that the line should cross through, and this is the y value of the point that the line should cross through. The slope moves it along, right? So since each one connects to its previous subfunction, we can see that this function, right, is only moving from 0 to 20. But where is it going to end? It's going to end at the x value of 20, which means the second function should start at the x value of 20, which is this guy. And this guy moves from the x value of 20 to 50. So since he ends at 50, this guy should start at 50, which is built into this point slope form. It moves from 50 to 92, which means this guy should start at 92. So this part, A, is much easier to find because it should always start at the previous x value. So A should be 92. Now, this value here is the y value of where the last one ended. Now, the y value would be the outcome of that x value. So since this guy goes to 20, if I plug 20 in, I would get the y value associated with him, right? And then this guy should start at that y value. So, let's check it. If I wanted to do 1/4 of 20, right, 1/4 of 20 is 5. So this guy is going to start at the x value of 0 and move to 20, and he's going to start at the y value of 0 and move to 5, which is why this next one starts at 5, right? When this guy goes to an x value of 50, if I plug 50 in, I'll get the y value that it ends. So 50 minus 20 is 30, right? 1/5 of 30 is 6. 6 plus 5 is 11. You can see that each case, it's going to end at the next value. So we don't know where this one ends because we don't know this value, but we can find it by plugging in 92 into this function and finding out the y value of it. That's where this guy is going to start. So that's what we need to do to find b. We're going to say 2/7 of x at its highest value, which is 92. Right, plus 11. Right, so 92 minus 50, which is 42, plus 11. Right. Now again, you can either do 42 times 2 and then divide that by 7, or you can say 7 goes into 42 6 times, and 6 times 2 is 12. Which means 12 plus 11 is 23, which is our b value. Because this function is going to go up to 23, which is going to be the start of the next function. So complete the equation. The equation is going to be 1/8. X is a value that we want to plug in, minus a is the x value that the last function started at. Right? Plus b, which is the y value where the last function started at. So there we go. This is the completed function for that last subfunction there. Okay. All right. So next part, they want us to graph this. Now, last lesson we talked about utilizing the space provided when we make graphs. We can fill in the x-axis and the y-axis however we would like, right? To make best use of this and to make sure it is as easy to read as it is to explain or describe, right? We would want to pick a scale for the x and the y value that would help ensure that we're using the space provided. So since we already worked through these values, we know that the lowest x value is 0 and the highest x value is 100. So somewhere here I'm going to have to go from 0 to 100, right? However I choose to space it, right? On the last one, we said that the function goes all the way up to 23, right? Which means that the highest this thing is going to go is 23 plus a little bit more, right? Because 23 is where this guy ended. We need to know how far this one goes up to before it ends. So if we want, we can try to figure out how high this goes so that we can scale this nicely. So if we wanted to, we could kind of do the same thing where we could plug in 100 and see how high this one goes. I mean, that's one way to do it. So if I said 1/8 times 100 minus 92 plus 23, right? If we put this all together, that's how high this is going. 100 minus 92 is just 8, right? 8 divided by 8 is just 1, so we can see that this one is going up to 24. So if you count it out, I mean, 1s aren't going to fit. This is going to go way off the chart, right? If I go by something like 5s, I'm not going to go very high before I reach 24, which is the highest. So I mean, you can kind of count it out and see. I already did count it out. I found that 2s would be a little too little, so 3s would be the best way to kind of make it fit. So I'm just going to count these by 3s. So you can see, I mean, 24 don't go right up to the end, but it's up near the top. I've made best use of the space provided. Right? Now here, if I work these out, I mean, I could probably space it out better, but I'm gonna kind of look here. I mean, 10s doesn't get us very far, right? We're gonna have a big empty space over here. But since the ends go to 20, 50, 100, counting by 5s would make it easier for me to place values on the graph. I mean, 92 is kind of a weird number, but we can deal with that. So I'm just going to count these out by 5s. $60, $65, $70, right? I know I need to get up to 100. I don't really need to label it any further past 100. Right, but I'll go into 105 just for good measure. Okay. So in order to graph a line, we know these are all linear functions. In order to graph a line, we know that each line just needs to be a connection of 2 points. Right? So doing this makes our life much easier because we can say that this first one is going to start at 0. When time is 0, he has biked no miles. That makes sense. The y-intercept is 0, right? And if you wanted to, you could go up 1 over 4. I mean, that's a slope, right? But we know that when x is 20, right, from what we did, right, this thing is going to go all the way over to 20. And when it's 20, it's going to come up here to this value, which is 5. So since we already kind of played with these values a little bit and recognized that, if we didn't recognize it right away, or if we were just asked to graph it, we could just plug in 20. I'm going to plug in 20. 20 divided by 4 is 5. So when I go to 20, I go up to 5, which is about there. We know it's a straight line, so I'm just going to make a line that goes from 0, 0 to 20, comma 5. We know that the next one is going to start at 25, right? Because this is point slope form, so it's starting at 25, which is this point. It's going to move to the next value. This one starts at 50, 11, right? So I can go over here at 50, come up here to 11, which is right about here. So I know that this guy is going to start where he ended and end where the next guy starts, right? So in point slope form, this works out to be pretty easy in our favor. And use the endpoints. Nobody wants to go up 2 over 7, especially when they're weird increments and it's very small. Very hard to do. So endpoint, connect the points with a line. We know that we've graphed that line. Right? The next one we know starts at 5011, which is here. Oh, dang, I put it at 45. 45. Let's just fix that real quick. And there we go. It's a little curved, but you get the idea. Okay. The next one's going to go from 5011, which is here, to, we said, what was it, 9223. So 90 is way over here. 2 is it's a little bit in here. Up to 23. I mean, this is 24. So 92. Maybe about right there. Maybe about right there. Now we can play connect the dots again, right? So this guy we said was 20 and 5, right? This one we said was 50 and 11. This one we said was 92 and what was it, 23? And then we need to go this last little bit, right? So from 92 to 100, so now we're going to 100 to 24 is that final little leg there of this, well, keep calling it a race, of the movement here, his bike ride. So this one was 100, 24. Right? Yeah, kind of like what we were talking about. We made good use of the space, vertically and horizontally. Having some leftover space isn't the end of the world, but it's definitely better than scrunching it all into right here. Now, if you were going to show this graph to somebody, nobody's going to have any idea what we are, right? It does tell us to leave our context, leave our axes in context. X's, we said, was time in minutes. Right? And the y-axis was the distance. And this one was in miles, right? There we go. There we go. Now we actually know what we're dealing with here. Right? All right. Now, number 7. Number 7, they focus on this second subfunction. And we've talked about some of this before. Right? But they just want us to look at the similarities and differences. Right? What are some of the similarities? What are some of the differences? We know that this is quadratic, right, because it's an x squared. This one is just linear, because it's a single version of x in point-slope form, right? We know that 20, 5 is a point that this line should go through. Just like when we were dealing with quadratics, we knew that 20 was a shift, 5 was a shift to get to the vertex of the quadratic. So here we can say that, both display a point of interest. Right? Of course, that point of interest is different for which one you're dealing with. And a coefficient, right? Which in this case is a fifth, the coefficient. 1/5 is the coefficient of our quadratic. And we know that those coefficients, a coefficient that affects its growth rate, right? We could say that. I mean, this one has a steady increase, growth. This one grew as a quadratic, right, like a U, but it still grew. It just grew at a faster pace, not a constant pace. So it does affect how it grows, right? In terms of differences, I'd say the main difference is that the first is a degree 1, right? Meaning that it's linear. That's probably the most obvious difference, right? While the second, right, is degree 2. Right? Which is quadratic. So they both have similar qualifications of how to get them graphed based on a point that is of interest to us, whether it just be some kind of random point on the line or the actual specific vertex of this value, right? Right? How does the point slope form of the linear function compare to the vertex form of a quadratic? Well, we can kind of base this on what we did with the quadratics, right? We can say that in this form, right, we are able to shift since we're comparing the point slope form of the linear, we can shift a basic linear function, right? So the basic function here was a function of slope 1/5. So like if we looked at just a linear function, right, like 1/5 x, right, where it has no y-intercept, so it starts at like the origin, then the point in the point slope form essentially moves this 1/5 sloped line to a new location, right? So we can shift the basic 1/5 x linear function right over to the point that the line should pass through. Right? Because point slope form literally means the point and the slope that we want on our line. So that the line should pass through that point, and it should have this slope, hence point slope form, right? So in the terms of shifting, we could say it went right 20, up 5, right? Now, in comparison to the quadratic function, right, the quadratic does essentially the same thing, right? It does shift in the same manner, right? But we're not just shifting just a point that we want it to go through, because the parabola, being a u, could pass through that point of interest at any certain time, right? So it does essentially the same thing, only that we shift, right, the vertex. And then, right, we can build the rest. Of the quadratic from there. Right? Because once we move the vertex, we use the a value. Remember, if we go out 1, up 2, up 4, right? So once we have the vertex where it's shifted, then we can build the rest of the function. So the idea of shifting is the same. It's just shifting a very specific point of a quadratic and then building the quadratic, or shifting a point of interest in the linear function, and then we're still building the linear function, which is off of the slope of 1/5. All right. All right, so let's look at another piecewise function here, right? Okay, so they give us a new piecewise function. We want to make a sketch of this. Okay, so this is a lot like how we were doing this in that first lesson with the absolute values, right? So I want you to try to pause and take a shot at this, right? Remember, use the domains to section off the graph, and then each of these is going to be graphed only in those sections. So I would recommend, pausing here and giving this a try, right? I'm going to go ahead and jump in here. Now we have an empty space here, so we can kind of see that the domain goes from -3 to 6, so it's a little lopsided, right? It's not all centered around 0. It's a little bit moving to the right. So personally, I'm just going to kind of center mine a little bit to the left here in terms of the y-axis, right? Because the left side needs to go to -3, the right side needs to go to 6, right? So it gives me a little bit more space here, okay? I'm not really sure how far up and down these are going to go just by looking at it, so I'm just going to kind of put it in the middle. Right? That'll give me some space up and down, right? But I've tried to center it, at least in terms of where the x's should be, right? So if I want, I can say from -3 to 0, 1, 2, 3, right? I'm just going to draw a real faint dotted line here to make sure I'm sectioning these pieces off in the correct manner. Up to 6. This one goes to 3, actually. 1, 2, 3. Right? Remember, the dotted lines aren't necessary, but it gives me a sense of where things should stop and where these things should start. Right? Okay. So, from -3 to 0, which is this little section here, I'm going to graph this line, right? Now, it's in the point slope form, which we just talked about is just shifting the line that has a slope of -1. So I'm going to try to use this format to graph it, right? If you're not sure, you could always distribute the negative, combine like terms, put this thing into y equals mx plus b form, and then come back over here and graph it. You could do that. But the way we were shifting it was, remember, this is like backwards from the way you see it. So this would be taking a shift to the left 3 units, up 4 units. So left 3 units, 1, 2, 3, up 4, 1, 2, 3, 4, places my point here. Right? Now, in terms of the domain, -3 is included, so I'm going to put this as a solid dot. If this was a strictly less than like this guy, that would be like an open dot. So, we may need to put some open dot, closed dots, so let's just try to keep that in mind. Once we have this point, it's a line with a slope of -1 that passes through that point. So from here, I can just go right 1, down 1, or down 1, right 1, right? Down 1, right 1, down 1, right 1, until I get to 0, because this is as far as I can go. So I know that this guy is going to be a nice straight line right there. All right, check. Okay. From 0 to 3, which is this next segment, it's just 1. So there's no x, right? This is just like a y equals 1. If we remember, y equals 1 is a horizontal line going through the y value of 1. So starting at 0, the y value is going to be 1, which is actually right here where this open dot is. So since this guy actually exists, I'm just going to go ahead and fill him in, right? Because he exists at 1, and he's going to be a horizontal line going all the way over to 3. So 3, open dot at 3, right? So it's going to be horizontal, moving over to the x value of 3, open dot. Right? This guy is another horizontal line at -3, which is down here at -3, but it's only existing from 3 to 6, so in this little interval here. So from 3, it's equal to -3, 1, 2, 3, closed dot, horizontal line, because it's just -3, until I get to the x value of 6, but since this is a strict less than, open dot. Open dot. There we go. So we're getting our first glimpse of kind of a random piecewise function here. We've always been using a piecewise function to kind of model like some person moving and stuff like that. So they actually all connect and things like that, but they don't have to. In this case, this function is just 3 random lines. They do conjoin in terms of the domain, right? So there's no like gaps in the domain, but nonetheless, we have this. Right? Each of the pieces are drawn independently through their functions, and this is what we got. Keep in mind the open dots and the closed dots, right? Very important now that we're scattering these things around a little bit. Okay. All right. So let's look at the next one. They want us to state the domain. Now, there's a couple different ways we can do this, right? They gave us the domains of each of the subfunctions. We know that domains go from smallest to largest. So we can say that starting with the smallest value, which is -3, and it continues on, right? Even though it goes up to 0 and doesn't include it, 0 is included here, so we don't have to stop it at 0. 0 exists. It goes from 0 to 3, even though 3 doesn't exist here, it exists here. So again, no need to stop at 3. We can just glaze right over it. But then it does stop at 6. So in terms of a inequality, we can say we like 3. 3 is included. Up to 6, but 6 is not included. So if we wanted to write it as an interval, it would go from -3 to 6. -3 would have a bracket because it's included. 6 would not have a bracket because it's not included. We would put a parenthesis on that. So if we wanted to write it as an interval, we can write it with the parentheses and the brackets where we need to, right? Otherwise, if we wanted to look at the graph, right, x's, domain means x's, so we can always use our pen, right? If we want the smallest possible x, which is way over to the right, the function is not getting over there, right? It's not getting over there. So the smallest x value that works will be the value where it finally touches our pen, which is at -3. Since this is a solid dot, we would include -3, right, in our domain, and this would start our interval. -3 is the first value that works, and then we can use our pen. As we move, is there any jumps, holes, or breaks in the graph? Not yet, until we get to here, right? This guy has an open dot, which means it's not included, but it does have a solid dot below it. So my pen will touch the line here at 3. So I can just skate right over it up until I get to 6 as an x value. 6 is not included. So I'm going to stop at 6, parenthesis, nothing past it. So that ends my domain. So you can always kind of use your pen in terms of your graph to kind of scan the graph. Where it stops, jumps, or breaks, we can kind of look at it, see if it's working or not. If not, stop the interval. If it does, keep going. All right? We'll circle back on that later on. All right. Now, we've already tried plugging these into here, right? So I don't really want to deal with that, right? But I am going to kind of circle back on these last two functions. But for these, I'm going to look at the graph to answer these, right? So when we look at this graph, right, if we want the x value of -1, then I can just go to the x value of -1 and see where my graph is at. At the x value of -1, I can go up and find out where the function exists. It exists right here, and then I can look at the y value that it goes with it. At the x value of -1, the function, which is this guy, is at the y value of 2. Otherwise, if I had this function, I could plug it in, right? -1 needs to meet the criteria of the domain. -1 falls in between -3 and 0. So I would plug -1 into here. -1 plus 3 is 2. The opposite of 2 is -2. -2 plus 4 is 2. So it still works. But if we have the graph, we can still look at it, right? I want the y that goes with that x. I want the y that goes with that x. So when I go over here to 5, 1, 2, 3, 4, 5. I'm going to find out where the function is, way down here. Once I reach that value, I can see what the y value is. The y value was -1, -2, -3. In terms of the function, if I want to plug in 5, I still got to pick the domain. 5 is in between 3 and 6. There is no x to plug it into, so the y value is always -3 when it's on this. So whether x is 4, x is 5, it's always going to be -3, which is why it still works there. Looking at the graph for the last one, I want to go to 3 on the x value. 1, 2, 3. Now, it doesn't exist here, so that's an open dot, meaning it doesn't work. But down here, it's a closed dot. So even though it's an open dot, it's not actually existing here. Closed dot means it does exist. So at 3, -1, -2, -3, that function, again, is -3. Right? Okay. Now, last one. Give this one a try. Give this one a try. Pause the video. Take a look at this. Make a graph. I'm going to put together the graph here in 1 second. You can just unpause it and watch me do it. So again, I'm going to start with the domains just to see. It's pretty centered, -2 to 3. So I'm going to center this guy pretty much right in the middle. Right? I don't see any reason to believe that it's lopsided vertically. So again, I'm going to put the x-axis kind of right in the middle. Okay. I'm going to section off the domains. Right? -2 is like here. I'm just going to draw it real light so I can kind of see where my function will start and end. You don't necessarily have to do this, but that's okay. I'm going to have another function in here from 1 to 3. Oh, dang, I put that at 4. 1, 2, 3. 3. 3. 1, 2, 3. So not this guy. And then I have another function that's beyond 3, right? Okay, so the first one, if I want to reorder this, I could. This would be -x² + 4. So this is just a standard position parabola, right? Standard position parabola moved up 4 units, right? So if I started at 4, 1, 2, 3, 4, because this is a vertical shift, this is going to be facing down. So if I go out 1, I'd be going down 1, out 1, down 1, out 2, down 4, 1, 2, 3, 4. Now, solid point here, open dot here. All right? So on this section, it's just this portion of the parabola that fits right here. See what I mean? Now, from 1 to 3, I'm going to use the point slope version of this to just shift my line. So it's shifting to 1, 3, because that's right 1, up 3, right 1, up 3. So that's going to be a closed dot, and it actually lands right on top of this one, so I can fill that guy back in. The coefficient is 1, so it's just a slope of 1 moved to this new direction. So I'm going to go up 1 over 1, up 1 over 1, open dot here. Open dot here. Right. Now this guy, that's again another horizontal line at 1, but it only starts when x is 3. So 1, 2, 3. The y value is always 1, so close dot at 1. And then it just keeps on going, right? This is unbound here. So this is just going to be a horizontal line that goes all the way off the graph out here like that. Right? So I segmented my graph to make sure I recognize what portions I want this thing to fall under. Graphing it just like we usually did, right? Last unit we did this. Up 4, right? Since it's a negative, we go out 1, down 1 instead. Out 2, down 4. I don't need to go further out here because I've already hit my line. Make sure you put closed dots and open dots where you need them. Right? If you want to use point slope form to shift to a new location and then use the slope to move it along, up 1 over 1, we can do it that way. That shouldn't be too bad. It's probably preferred, especially for piecewise functions, because we have these segments, right? Just a single value is a horizontal line for whatever x's that we need. So there we go. All right.